graphic matroids.
Cool. Thanks, Spencer. And actually, maybe I can add to that sentiment, because at lunch I was talking to some PhD students who hadn't really encountered Matroids before, and that's a tough situation to be in at a conference like this. So if you have any questions about Matroids, just come and talk to me or Rutger, or I'm sure there are a dozen people in this room who would be very happy to talk to you about any Matroidal stuff. If you have any questions, don't be shy. Okay, let me carry on. So this is work with Darryl Funk, who was formerly a postdoc working with me in Wellington and has now returned to his hometown of Vancouver. And everything that I'm going to talk about is, almost everything I'm going to talk about is work that we have done together over the last several years, or work that we intend to do together over the next several years. So any theorem for which I don't have an attribution is joint work between me and Darryl, or it's work in progress with me and Darryl. So here's what I want to do with this slide. This tower of blocks is kind of a blueprint of what we have been doing and what we intend to do. So the bottom three blocks form a foundation. The bottom three blocks form what I'm going to call a representation theorem, and then the blocks at the top will give us applications of that representation theorem. So I'm going to start, I want to explain every block, at least briefly, so I'll start at the bottom. And to explain the bottom block, I need to talk about bias graphs and signed graphs. So this is what a theta subgraph looks like. A theta subgraph consists of two distinct vertices joined by three paths, where the three paths have no internal vertices in common. Now, a biased graph is just a graph with extra structure, so a graph with a distinguished collection of cycles. So we call those cycles the balanced cycles. And the collection of balanced cycles can be almost arbitrary, but there is one rule. I insist that in any theta subgraph, I am not allowed precisely two balanced cycles. So I look at any theta subgraph, I am allowed 0 balanced cycles, or 1 or 3, but not 2. That's the only requirement to have a biased graph. A biased graph consists of a graph along with a collection of balanced cycles satisfying that requirement. In many cases, there is no particular structure to the balanced cycles, but in some cases we want to think about the balanced cycles that come from a labeling of the edges. So H is going to be a group, and I'm going to label the edges of the graph with elements from H, group elements from H. I'm also going to direct every edge in the cycle, in the graph, and now this structure tells me which cycles are balanced and which cycles are unbalanced. So I take a cycle, and to find out whether I want it to be balanced or not, I walk around it. And I take the product of the edge labels as I go. And I just remember that if the direction of the edge is going against my direction of travel around the cycle, I won't use that edge label in the product. I will use its inverse instead. Okay, so in this example, I have labeled the edges with elements from the group S3. So those are permutations of the set 1, 2, 3, expressed in cyclic notation. And I'm going to construct a product as I go around a cycle. The product going around a cycle may not be well defined. It may depend on my choice of starting point, and it may depend on my choice of direction around the cycle. But if the product is the identity, it will always be the identity, no matter what direction I choose, no matter what starting point I choose. So let's look in this example at a cycle that gives me the identity. If I start at the bottom left and I go clockwise, then I take 1, 3, and then I'll multiply that by the permutation 1, 2, 3. No, I'm sorry, I won't, will I? Because I take the inverse of 1, 2, 3. Because as I walk clockwise, I'm going against that edge. So I take the inverse of 1, 2, 3, which is 1, 3, 2. The product of 1, 3 and 1, 3, 2 is the transposition 1, 2. And as I walk along that final edge at the bottom, I take the product of 1, 2 with 1, 2, and that's the identity, because 1, 2 is its own inverse. So that is a cycle whose product is the identity, and I'm going to declare those cycles to be balanced. So those are the balanced cycles, the cycles where I have a product equal to the identity. This cycle, on the other hand, if I start from bottom left and I walk clockwise, I get 2, 3 times the identity times the inverse of 1, 3. 1, 3 is its own inverse. So I just have 2, 3 times 1, 3, and that is not the identity. This is an unbalanced cycle. Okay, so far we have biased graphs, which are graphs with a distinguished collection of balanced cycles, and we have gain graphs. These are the biased graphs that arise from group labelings. And if I want to be specific about the group, I will say that this is an H-gain graph. So the pattern of balanced and unbalanced cycles arises from labeling with elements from the group H. If the group H is the group with 2 elements, then I'll say that I have a signed graph. And of course, in that group, every element is its own inverse, so I can forget about the directions of the edges. All I'm really doing is I'm picking out a special set of edges. Those are the edges that are labeled with the non-identity element. So I'll say that sigma is that set of edges. That's the set of edges labeled with a non-identity. And now a cycle is balanced if and only if it contains an even number of edges from sigma. So when I draw a signed graph, I'm going to mark the edges in sigma in blue. We'll be seeing drawings like this a few times. Okay, so that's enough background for the bottom block in my tower. Now I can talk about the situation where I have some biased graph that is not signed graphic, but I have some very large number of vertices V with the property that if I delete any such vertex V, I get a biased graph that is signed graphic. So it is not signed graphic, but there are many vertices whose deletion makes it signed graphic. What must that structure look like? I'm also going to impose a mild connectivity condition. I won't say anything more about that, but just think of it as being like analogous to 3 connectivity in a graph. So roughly speaking, I've got a 3-connected biased graph. It is not signed graphic. It has many vertices whose deletion makes it signed graphic. It has to be one of these 2 structures. I've got what we call a blobby theta or a coracle. These look like signed graphic pictures because I've illustrated some edges in blue, but actually they're not signed graphic because of some extra unbalanced cycles. So any cycle that uses 2 branches of the blobby theta has to be unbalanced. Any cycle that uses all the vertices around the outside of the coracle, that must be unbalanced. Yep. The only condition for the collection of balanced cycles is that a theta subgraph is not allowed to contain precisely 2 balanced cycles. Okay? So I do have 2 biased graphs here. They are not signed graphic, but if I delete any of these marked vertices, I will get something that is signed graphic. So these are the only 2 structures that satisfy that condition. They give me many vertices whose deletion gives me something signed graphic. So that's the bottom block of our tower. So now I'm going to move on to the second block. To talk about the second block, I need to talk about frame matroids. So frame matroids are similar to graphic matroids. So remember, a graphic matroid has as its ground set the set of edges for the graph, and all the cycles of the graph are dependent in the matroid. Well, this is similar in a frame matroid, but I am going to allow some of the cycles to be independent. So I'm going to relax some of the cycles into being independent. When am I allowed to do this? Well, basically, when I have a biased graph, because the balanced cycles are exactly the cycles that remain dependent. That's why I need that condition on the theta subgraph. Otherwise, I would violate the circuit elimination axiom for matroids. Okay, so I start with a biased graph. The frame matroid has as its ground set the set of edges. And the dependent sets of that frame matroid are exactly the sets that contain a balanced cycle or that contain a connected subgraph with at least 2 cycles. That now defines the matroid. Some special cases are familiar. If every cycle is balanced, then obviously it's just a graphic matroid because every cycle is now dependent. If no cycle is balanced, then we get what we call a bicircular matroid. Okay, so this conversation shows that every graphic matroid is a frame matroid, right? Because I can simply make every cycle balanced. And now I have a frame matroid that is also a graphic matroid. But there are other ways of getting graphic frame matroids. There are other biased graphs which give me a graphic frame matroid, even though there are unbalanced cycles. So even though there are unbalanced cycles, the frame matroid may be a graphic matroid. And that can happen in precisely 6 scenarios. So 5 of them are given by this theorem by Rongchen, Matt DeVos, Darrell Funk, and René Pivotto. So these are 5 pictures, and note that 4 of them are signed graphic. All of them are signed graphic apart from the fat theta. Every other one has some shading, which tells you which edges belong to that distinguished set, the set sigma. So a cycle is balanced if and only if it contains an even number of shaded edges. So that's going to be relevant. Okay, so there are 6 cases here, right? The 5 given by this theorem and the case where every cycle is balanced. Those are the ways that a frame matroid can be a graphic matroid. Now that's relevant for my second block, because what I want to do in the second block in the tower is talk about the situation where I have a biased graph whose frame matroid is not a graphic matroid, but there are some very large number of vertices such that when I delete one of those vertices, I get a biased graph whose frame matroid is graphic. So I have a scenario where the frame matroid is not graphic, but deleting one of some very large number of vertices produces a biased graph whose frame matroid is graphic. Again, I have the mild connectivity conditions. There are 5 structures that have this property, given by these pictures here. You can kind of see that we painted ourselves into a corner a little bit with the names, because we discovered the buckle and the belt, and then as we discovered further families, it seemed as though we had to keep on giving them names, starting with B, matching up with things that you wear around your body. I'm hoping that we won't find too many more families because we're running out of names. But if you have any suggestions, I'd be happy to brainstorm with you. Okay, so this is the second block. A biased graph has a frame matroid that's not graphic, but it is close to being graphic in some sense. Many vertices give you something graphic. The reason that the first block is important is because if I delete a vertex and see something graphic, probably that graphic thing is going to be a signed graphic bias graph. So if the thing that I start from, the bias graph that I start from, is not signed graphic, then I'll be able to apply the theorem in the first block, because I'll have many vertices which reveal something signed graphic. And then I know exactly what the structure is, so I can use the first block as a foundation. If it's not the case, then the omega in this theorem, the bias graph I start from, is already signed graphic, and that simplifies the analysis quite a lot. So the first block simplifies the analysis here considerably. So why do we care about this? We care about it because frame matroids can be represented by a large number of different bias graphs. This is a problem. It's always a problem in matroid theory when a matroid can be represented in many different ways. It makes it much harder to analyze that class. So the talk, in Jeff's talk, when he was talking about a stabilizer, what that stabilizer was doing was controlling different representations. That's what we want to do for frame matroids. We want to get control over the different representations. So we use the idea of a committed vertex. Say omega is a biased graph and V is a vertex in that biased graph. Now I'm going to move to some completely different biased graph representation of the same frame matroid. So I'll move to omega prime, a different biased graph which has the same frame matroid. Now imagine that no matter which biased graph I move to, if it's representing the same matroid, then the set of edges incident with V in omega is incident with some vertex in omega prime, no matter what omega prime is, if it's representing the same frame matroid. So that means that the vertex star at V, the set of edges incident with V, always looks like a vertex, no matter which representation I move to. That's what I mean when I say that the vertex is committed. It is committed to being a vertex. Not every vertex is committed. I can look at a bias graph and move to a different bias graph representation of the same frame matroid, and that vertex star, that set of edges, may have been smeared all across the bias graph and may have completely evaporated. It doesn't look like a vertex at all. In that case, the vertex would be uncommitted. So committed vertices are our friends. Uncommitted vertices make life hard. So we want to get control over the uncommitted vertices. So that's what we do in the third block. We consider the case that I have some bias graph with a very large number of uncommitted vertices. And there are 6 structures that can give us this outcome. 5 of them we saw before, the ones that start with B, and then the twisted flip, which Darrell discovered in his thesis. Okay, so that's what we call the representation theorem. The bottom 3 blocks of our castle give us control over different representations. With sufficient control over representations, we should be able to move to our applications. So the first application, well, maybe not the first, but the most notable application being Rota's conjecture. So many of you will know what Rota's conjecture says, some of you may not. Rota conjectured that if F is a finite field, then I look at the class of matroids representable over F. That is a minor closed class, so I can ask for the minimal obstructions for that field, the excluded minors for that class. Rota conjectured that there can be only finitely many of them. This is now resolved by Dillon, Gerhard-Zwittel. What's the analog for gain graphic classes? Let H be a finite group. Consider the class of frame matroids arising from H-gain graphs. Those are the H-gain graphic matroids. So those, I'll say that again, frame matroids arising from the bias graphs, which are in themselves produced by labeling the edges with elements from the group H. So let's conjecture that such a class has only got finitely many excluded minors. So we should have a path towards this theorem. So one of the ingredients will be a proof that Darrell gave fairly recently with Luis Godin and Matt DeVos that there are only finitely many excluded minors for bicircular matroids. One of the key ingredients of that proof is control over different representations of bicircular matroids. We have exceptionally good control over the different ways that bicircular matroids can be represented. Now, with our representation theorem, we should have adequate control over the different representations of H-gain graphic matroids. So if we take the strategy from the bicircular proof and combine it with our representation theorem, it is reasonable to believe that we have a path towards Rota's conjecture for gain graphic matroids. So I won't say too much more about Rota's conjecture. I'll instead talk about this other application to monadic definability. So monadic second-order logic is a formal logical language. It arises very frequently in discrete mathematics applications because it has these very natural and strong connections to complexity theory. So in monadic second-order logic for matroids, you have these variables that represent subsets of the ground set, and you have a predicate which allows you to say when one subset is contained in another. You have another predicate which allows you to say when a subset is independent. And then you have the things that you would expect to see in a first-year logic course. So you would expect to see the logical operators, negation, conjunction, disjunction, implication, and you would expect to see the universal and the existential quantifier. So from those ingredients, we can construct sentences, and we ask, when is it that a class of matroids can be characterized by such a sentence in this language? So, yes, go ahead. No, unrestricted quantification. So if I have a class of matroids and there exists some sentence in this language which is satisfied by exactly the matroids in that class, then I'll say that the class is monadically definable. And it is because of these connections to complexity theory and the theory of computation, it is natural to ask, when is a class of matroids monadically definable? So here's an answer to one problem. This is a theorem that I did with Mike Newman and Jeff Whittle. Let F be a field. The class of F representable matroids is monadically definable if and only if the field is finite. So this entire project is really about finding analogues for gain graphic classes of matroids. So what about the equivalent question for H gain graphic classes? So here's a theorem. If H is a finite group, then the class of H gain graphic matroids is monadically definable. So one direction holds, and the other direction is false. So if H is an infinite group, then the class of H gain graphic matroids may or may not be monadically definable, which I think is actually a more interesting situation than if the analog for fields held. This problem is very seductive. Okay, so this Venn diagram that I've put up is a Venn diagram of all infinite groups. I've drawn two circles, ellipses. Inside the left-hand circle, I've got all the groups with finite exponent, which means that you cannot have elements of arbitrarily high order in the group. In the right-hand circle, I've got all the groups that are locally finite. That means that any finitely generated subgroup is itself finite. If you are not in the intersection, if H is not in the intersection, then the class of H gain graphic matroids is not monadically definable. We know that much. But there are some infinite groups for which the class of gain graphic matroids is monadically definable. So this is work that I did with Sapir Ben-Shahar last year, which was her senior project year. So we have constructed a hierarchy of infinite groups built using infinite direct products and semi-direct products. If H belongs to this hierarchy, then the class of H gain graphic matroids is monadically definable. But there's still this gap between the blue and the red. The blue represents the classes where we have definability. Red represents non-definability. So what's the boundary between blue and red? I was talking about that problem in Leeds earlier this year, and Angus Matthews, who is a first-year PhD student, became very interested in the problem and has made some really nice progress. It was going to look a little underwhelming when I put his progress on the Venn diagram, but it's not. That's a pretty significant red dot. So Angus has discovered a concrete construction of some infinite group. It is locally finite, and it does have finite exponent, and yet the class of H gain graphic matroids is not monadically definable. So knowing that there is red, having a concrete construction of a group in that, a red group in that space is very nice. And it makes me hopeful that we might one day be able to find the real boundary between red and blue. I'll end with a quick progress report of how we're actually getting on with constructing this tower. So the bottom block, it's mainly written up. Hope to get it submitted this year. I'll say that it's 80% complete. The next block is much bigger. We have got a lot written down, but there are still some cases to analyze. I'm not too frightened of them, but it will take work. I'll say that's about 60% complete. The top block, I believe we've got all the right ideas. It's going to take work to put them together. It's about 50%. Rota's conjecture, I again believe that we have a pathway, but we will still have many technicalities and probably some conceptual hurdles to overcome, so that's more like a 20%. Monadic definability for finite groups should be easy once we have the representation theory. There will be more technical work to do, but it's only technicalities, so that's like a 75%. And monadic definability for infinite groups, well, I don't truly have a good conjecture right now, so I can't really say that it's close to completion, maybe 25%. So I'll probably see you all in another few years, and hopefully these bars will have moved a little bit further to the right. Okay, I'll stop there, thanks.
Great. Thanks, Dylan. Question?
How do you define non-definability? It's really hard. It uses an analog of the Myhill-Nerode technique for regular languages. If that means something to you, that's great. If not, let's talk about it over coffee sometime. It is something... Yep, I'm confident in that. Yeah, let's talk some more. There's only one I have only one technique. I wish I had more, but I've only got one technique. It doesn't always work. Hopefully it will be enough. Yep.
Is the previous theorem depending on the Rota's conjecture? So do you know?
No. So this work does not depend on the work that Jim and Jeff have done. Is that what you mean?
The Newman and Jeff about representability.
Oh, definability.
Yeah.
No. It uses the same techniques. It does not depend on the work that I did with Jeff and Mike for field representations. It's Thank you. Yes. The theorem by myself and Mike and Jeff uses Rota's conjecture in one direction. If the field is finite, then there are finitely many excluded minors. Yeah, sorry, I misunderstood what you were saying. Then you have finitely many excluded minors, and that in turn implies monadic definability. Yeah, now that's a really interesting question. Can you prove monadic definability without relying on the excluded minors? I don't see how, but I think it's interesting.
Any other questions? Okay, if not, let's thank Jonathan.
Thank you.